Thanks for the introduction. And hello, my name is Jaewon Kwon, and I'm from Yonsei University. Today, I'll talk about Garibaldi, a pairwise instruction data management for enhancing shared last level cache performance in server workloads, which is a collaboration with my co-professor Yongju Lee and our colleague at Yonsei University. Recent server workloads leverage deeper and more complex software stack. As a result, the instruction footprint in the memory hierarchy has grown substantially and decreased instruction cache performance. Thus, server workloads are characterized as significant front-end bottlenecks, as shown in the orange part of this graph from the ISCA'25 paper. Naturally, many works targeting the instruction footprint of server workloads, including better branch prediction and its metadata management, and instruction prefetching that integrated into pipeline or using its information, and L2 instruction partitioning using pipeline events for more instruction-intensive workloads. However, LLC is different. LLC, which is shared among all cores and physically distant from the pipeline, it is difficult to attribute the individual cores LLC performance to the individual cores pipeline, and it making hard to measure the cost of instruction misses. As a result, LLC was not considered to extend these techniques. On the other side, there were traditional schemes for large data footprint, and among them, the modern LLC management already able to get Oracle-like performance in data caching. For example, the Mockingjay successfully combined the PC-based reuse distance predictor and Baladi's optimal replacement policy, and they evict the line based on the predict time of reuse and emulate the Baladi's optimal replacement policy. However, they do not consider the impact of the instruction line on data access, and why this is a new challenge for LLC management. We first drive the CPI stack breakdown by simulating a 40-core system, and as shown in the top graph, the traditional workload like spec have a negligible instruction footprint in the LLC, so instruction cache line have almost no impact on overall cache management. However, as shown in the bottom graph, server workload exhibit exact opposite behavior. Even with modern branch predictor and instruction prefetcher, the instruction misses are not fully eliminated and still reach the LLC. Even worse, under the reuse distance LLC management, including Mockingjay, instructions in the LLC are more likely to be victim of contention than the data, which we call the instruction victim phenomenon. The right-hand figure illustrates how the contention from increasing core counts affect the caching of instruction and data line. In here, reuse distance counts the number of distinct access to the set of shared LLC between two hits to the same line. As the core counts increase to 40, the average reuse distance of instruction line exceeds the LLC weights in all workloads, whereas data line, even after the contention, their reuse distance is still under the LLC associativity. Thus, instructions are more likely to be victim of LLC contention than data. The instruction victim effect from the LLC access pattern of multi-core server workloads. The server workload exhibit high instruction access ratio, however, they exhibit smaller access counts per cache line compared to spec workloads. This means there are many core instruction lines in the server workloads. On the other hand, for each data line, the frequent data access indicate that server workloads have a few hot data, and as a result, the reuse distance plus shows that the data in the server workloads have much shorter reuse distance than those of the spec workloads. And combined together, in server workloads, many core instructions access leads to access to a few hot data, which we called many to few access pattern. Without recognizing this pattern, today's LLC policy keep hot data but evict most instructions. To evaluate the true potential benefit of reducing instruction misses in server workloads, we conduct an Oracle study where instructions always hit in the LLC after their first access. In spec workloads, Mockingjay achieves a modest 8.4 performance gain over the LLU, almost achieving the 9% of iCache Oracle. On the other hand, in few cases of server workloads, Mockingjay achieves 6.3 performance improvement over LLU, while Mockingjay with iOracle achieves 41 or 42% performance gain, that means there is significant headroom for an instruction footprint area LLC management in several workloads. We investigate the mechanism of instruction victim problem in several workloads with many to few access pattern. And instruction cache line might have multiple instructions that access different cache line. And in several workloads with substantial data sharing, the data line accessed by multiple instructions are likely to be remain because of their hardness. In contrast, instruction cache line might be evicted because they are not reused for the long time after the first accesses. For these reasons, in a many to few access pattern, cold instruction line is followed by hot data lines. This is problematic because even the hot data access depends on fetching cold instruction lines to trigger them. And to examine this relationship, we analyze the miss rate of instruction cache line based on whether their associative data lines are hit or result in hit or misses. And surprisingly, the instruction miss rate associated with hot data access are higher than those associated with cold data access in almost all server workloads. That means data hardness is not naturally conveyed to the corresponding instruction line. What happens if a data hardness is not conveyed to the instructions? In server workloads, the cold instruction line miss, and it incurs the front-end pipeline stir, and it delay the address generation and issue, which eventually delay the hot data access, which is already cached. For that delay, cache can't utilize the hot data they have. Thus, the cost of LLC instruction line miss can be thought of opportunity cost of delayed hot data access, and thus more delay the hot data access is more costly given instruction line access. So let's move on to our proposal. So we propose Garibaldi, a pairwise LLC instruction data LLC management scheme. First, we selectively protect the instructions that access critical hot data lines, and second, we compensate for increased data line miss by prefetching the paired data on the instruction misses. Ultimately, both mechanisms converge on a single goal: conveying each data line's hardness onto each corresponding instruction line in the LLC. To do so, we first define a metric that correlates the data hardness with instruction miss in the LLC. The core insight is the opportunity cost introduced in the motivation. We leveraged the existing LLC management scheme, which already performed near Oracle-like classification of data as a hot or cold. The cache status in this cache hit status in this policy exhibit 90 to 99% similarity to the hot data set defined by those that will be reused with the perfect knowledge. In our framework, so the data access resulting in cache hit in the LLC are classified as hot, while those resulting in miss are deemed cold. So this classification enables seamless integration with existing policy because we don't need the separate definition. To implement this correlation, we introduce a pair table that tracks the instruction data pairs and uses this information to quantify the cost of each instruction line miss. We employ the n-bit saturating counter for each instruction line in the LLC, which is dynamically adjusted. Incremented when the paired data access hit and decremented otherwise. Using this metric, the first of pairwise management is to selective instruction protection. For instructions that access to important data, we selectively protect this. The method for implementing this is query-based protection. It was inspired by the QBS paper from the different problem. And during the eviction, if the eviction candidate C in this figure is the instruction cache line, and we read the miscost from the pair table. And if the miscost exceeds the threshold, protect this, and we move to the next victim D in here. In this figure, instruction line D's miscost does not satisfy this, thus we evict D. To complement the compensated data misses, we leverage pair information to prefetch unprotected cold pairs. If an instruction is not protected, that means its pair data lines are likely cold. Thus, we overlap the instruction miss penalty with data miss penalty. In this, so paired data line prefetch is triggered on the instruction line miss. In this figure, instruction line D was evicted earlier because its miss cost was low. When it was assessed again, and that miss cost an ifetch store. While the instruction is already in the flight, we read the pair table of the instruction line and we get the address of paired data line E and F. Using that information, we issue the prefetch, which effectively hides the data miss latency and ongoing ifetch under ongoing ifetch stores. Now I'll talk about the hardware support. Right figure is showing the memory hierarchy and Garibaldi related support lies on the LRC. In the right figure, the shaded area indicate the added component in the LRC controller, and Garibaldi management is implemented as a 3 pair table operations, like allocation and update, and query, and pairwise prefetch. This figure details the pair table and its management unit, and it illustrates that the ITLB-like hypertable that records the PC to ILPA mapping during the NRC instruction line accesses, and it enables subsequent data access to locate corresponding pair table instruction with PC. And dynamic management adjusts the protection threshold and its aged miss cost, and decoupled the DPPN optimized storage by sharing common address bit. You can refer to our paper about detailed storage configuration, and the storage overhead is below 1% of LRC capacity. And based on our cacti modeling, we set the pair table lookup cost to 1 cycle and max attempt to 2 cycles. That means capping the worst case eviction overhead at 2 cycles. Now let's move on to the result. We evaluate our design using 2-step approach. First, we run each workload in Gen5 full system mode to capture the complex software stack of several workloads, and then we feed that instruction trace into SniperSim, which gives us the cycle level accuracy for many core system with practical runtime. For the baseline, we model the Intel Sierra Fresk like 40-core system with Tage, branch predictor, and ISPy and GHB prefetcher, and we implement non-inclusive shared LRC with LLU and compare the several LRC management scheme, including Mockingjay, Hawkeye, and DRLib. We orthogonally combine Garibaldi to them. And for workloads, we choose 16 popular workloads. For details of the methodology, please refer to the paper. We first conduct an end-to-end performance comparison between state-of-the-art reuse distance-based LRC management policies and Garibaldi. You can see that Garibaldi makes substantial performance gain. One interesting trend here is that as the instruction victim phenomenon become more prominent, the performance gap between the Hawkeye and Mockingjay diminishes as the Mockingjay's advantage in better data caching is offset by the delay caused by the instruction victimization. In that case, the Garibaldi's gain increased more and offset the diminished data caching return. Now we show you the quantitative correlation of speed up at top graph and the ifetch stir cycle reduction at bottom graph. First, speed up track the ifetch stir cycle reduction, and workloads like validator with highly reduced ifetch stirs see the largest gain. And second, the performance gain varies across the workloads in proportion to their ifetch stir reduction. In the negative case, like Kafka, the both instruction and data are cold. So Garibaldi still cut the ifetch stars. The extra data means outweighed that benefit, so that becomes the negative case. On the average, Mockingjay alone reduced the ifetch stir cycle by 9%, and adding Garibaldi doubles this to 18% reduction. And energy saving mirrors the stir saving. Now I'll conclude my talk. So we observed that shared LLCs evict the instruction line far more often than data, and stalling front end of the server class CPU. The key insight is the worst instruction miss happens when the data soon it touches is already hot in the LLC. Yet, that hotness is never related back to the instruction line. Thus, we propose Garibaldi that treat the pairs and selectively protect the instruction from hot pairs and complement this by prefetch data from cold pairs. Our evaluation shows that Garibaldi achieves 13% gain over LLU and an additional 6% on the top of Mockingjay, and you can see the seamlessly complementing existing state-of-the-art policies. That's the end of my talk, and thank you for your listening.